In this lecture, I want to talk about soap, I guess. I didn't know that when I became a professor, this would be one of my favorite topics to talk about, but the chemistry is so good, and obviously it's very relevant. And so uh, let's go for it, I guess. Okay, so related to what we've been talking about last time, let's just remind ourselves what hydrogen bonding is. So sometimes people call it hydrogen bonding, sometimes they call it hydrogen bonds. This is when we see a dipole-dipole interaction where one of the interacting elements is a hydrogen atom. And let's pick on water. That's probably the most important hydrogen bonding molecule out there. We'll just show a few hydrogen bonding interactions. And I'm going to abbreviate those as H bonds. So our hydrogen bonds are our H bonds, and they're shown with these dashed lines, connecting oxygens from one water molecule, which are electronegative, to the electropositive hydrogen elements on a separate molecule, and similarly, the electropositive hydrogen elements connect to oxygens. And so we have this arrangement of hydrogen bonds, very powerful molecular properties, biological properties, whatever, material properties, I should add. You can take advantage of this all across whatever we're trying to accomplish as humans or biological systems. It's important. Water forms a strong H bonding network, and we should recognize that, and we should not forget that. And again, H bonding is hydrogen bonding. Okay. With that in mind, as sort of a refresher, let's start to think about what happens when we add water to other things. So anything that water dissolves, or anything that dissolves in water, is generally forming hydrogen bonds with that water. So if you think about all the things like salt, sugar, ethanol, whatever, these things that you can mix in with water, and at the end of the day, you get like this clear solution as the material has dissolved. What happened is, if you take salt, those crystals have been broken down by the water molecules into their respective ions. So you have some Na plus floating around, some Cl minus floating around, and it's all interacting with the water molecules through hydrogen bonding networks. Like the chlorines are interacting with the electropositive hydrogens, and the Na is interacting with the electronegative oxygen atoms. I guess those aren't technically hydrogen bonds, but it's involved. We're taking advantage of the electropositive and the delta positive hydrogen atoms in water as we dissolve certain things. Now, we can take advantage of that when we look at soap. So soap is kind of built up, and really we're going to focus, this could be much more complicated, but let's focus on what's called a simple detergent. A simple detergent. So soap, and this is kind of a common detergent. Let's talk about a fatty acid detergent. So fatty acids are things that are, I guess, derived from biological fats or waxes in the body. Now, what they have is this general structure. Don't worry about the length of the hydrocarbon chain here. Just draw a really long zigzag that ends with a carboxylic acid. The carboxylic acid is a functional group where a carbon is simultaneously double bonded to an oxygen and single bonded to an OH group. Okay, so this is a fatty acid detergent. Let's look at how it works. Well, if I just redraw that structure, and again, today is not the day where you worry about recreating the perfect number of carbon atoms. It's just a long chain of carbons, and we're going to pick on one without any branch points. But I'm using two colors to indicate the two regions of our fatty acid detergent. We have the non-polar tail, okay, the nonpolar tail. And the nonpolar tail does not dissolve in water. Okay, so it doesn't dissolve in water. Now, over here at the orange, we have the polar head. So the tail is sort of in quotes. Obviously, that's just us trying to wrap our minds around these structures. We have this polar head. This polar head, you can see, has electronegative oxygen atoms and an electropositive hydrogen atom. It's a hydrogen that's attached to an electronegative atom. We would call that maybe an acidic hydrogen, and that's where I said the carboxylic acid functional group. It's where the acid suffix actually comes from. So this does dissolve in water. So we see this kind of dichotomy this molecule has. It doesn't, if you mix it with water, it's not sure if it's going to dissolve or not dissolve. You could say like half of it doesn't dissolve and the other half does dissolve, but let's be serious. The nonpolar hydrocarbon tail is actually quite a bit bigger than the polar head. So the majority of the molecule doesn't dissolve in water. And let's clarify, this does dissolve in water using hydrogen bonding. And hopefully you can kind of see where that comes from. We have the that head group has oxygens and hydrogens that can interact with the oxygen and hydrogen water molecules through dipole-dipole interactions. And so what we're going to do is we're going to mix this with H2O. Now, when we mix this with H2O, what we have is these two regions, one that does dissolve and one that doesn't dissolve. I'm going to clarify that the part that doesn't dissolve is hydrophobic. It is kind of living in fear or antagonized by the presence of water, or it's water avoiding. Okay, so that purple region is water avoiding. Now this part that does dissolve is hydrophilic. And this is, I'll get very gushy here. It's water loving. It really kind of means has affinity towards something, this philic or phile suffix. Some people like to say loving, which is fine. It's more like affinity, but whatever. So it has some affinity. It's willing to engage with, that sort of thing. So I'm going to mix this together. And let me clarify, these are important terms, hydrophobic and hydrophilic. It's definitely good for the toolbox. When we mix this with water, we've got one region that wants to avoid water at all costs. We have another region that's happy to interact with it. And what we get is something like this, where let me just draw the detergent. I'm just sort of redrawing this. I have my tail now that's a little bit less defined. And then I have my head group. And this is a shortcut or kind of abbreviation for the polar head. And this is the nonpolar tail. Okay. So this is me abbreviating the structure so it's a little bit more manageable because I'm about to draw at least 20 of these things. So I haven't quite gotten to the water yet. So let's just say, kind of have our arrow intersecting that. So that's me abbreviating that structure a bit. Now what I'm going to do is I'm going to draw a two-dimensional cutout of a sphere. So what I'm drawing is going to look like a circle. It's a circle that's outlined with circles, but in reality, it is a sphere. Now, what these circles are is, I'm just going to highlight one of them because you may not want, you could go ahead and do that, but you may not want to because it's a lot of ink. We can capture the main point. We're going to put these heads, the polar heads, around the outside, and then on the inside, we're going to have the nonpolar tails sort of interweaving inside within this spherical object. This would be, first of all, it's really a sphere. Second of all, the tails, which I should highlight one as being purple if I'm going to highlight one head, it's really a sphere. It has heads on the outside. and tails on the inside of the sphere. And the outside of the sphere is interacting with water molecules. And what this is called is, this has a special name. This is called a micelle, a spherical structure with two sort of phases. One phase that can interact with the bulk solvent, which in this case is the water. Just the enormous amount of water is interacting only with the outside surface of our sphere. Then on the inside, we have a different sort of phase, if you will, something that, yeah, is just doesn't have an interaction, an ability to productively interact with our bulk solvent, which is in this case water. You could build all sorts of micelles. You can build micelles within micelles, but this is just a very simple micelle derived from a fatty acid detergent, but it has some really cool properties. Because the outside surface will interact with water, the micelle can dissolve in water. Okay, so all I'm saying is we have a hydrogen bonding ability of all of the water molecules to the outside surface, the carboxylic acid heads of our micelle. But something is interesting that's happening inside. The inside is hydrophobic and will dissolve / productively interact with things that don't dissolve in water. What are some common things that don't dissolve in water? So, or mix with water, sure. Like oil, right? People talk about oil not mixing with water. You see two phases. So oil and water. If you mix them together, you see two phases. It's something that we'll see in, we will have kind of seen in lab 6 as the product of our reaction actually comes over with a little bit of water, and the water kind of makes everything foggy because it doesn't dissolve and become a clear solution. Anyway, the hydrophobic region of our micelle will actually have the capability of dissolving things that don't typically dissolve in water. Well, oil is one thing. What's another example of something that doesn't dissolve in water? A really good one is kind of dirt, grease, grime. Okay, think about an experiment that we've all done. Like we're doing something and our hands get dirty. Here's our hand. And let's get it dirty. Let's put some grease on it. And we go over to the sink and we're like, shoot, we're out of soap, or maybe we're not in a good place for soap, or whatever. There's a reason why there's no soap around. So we're going to do a chemical reaction where we just turn on the faucet and try to rinse off the grease or grime from our hand, or maybe our dirty dishes, whatever. And when you do the experiment, you find that the outcome is no transformation of matter. Our hand still has the majority of the grease. Now, maybe the force of the water knocked things off, but there wasn't like that nice feeling of dissolving. Like sometimes you get something on your hands and you can just rinse it with water and it's gone. It's a good feeling, like, you know, a little bit of salt or something. I don't know. So we had some grease on our hands. It didn't come off with the water. The reason why was, other than just a forceful interaction with some water droplets coming out of the sink, we didn't see hydrogen bonding or an affinity of the grease with water. I mean, grease is more oily anyway, so that kind of makes sense. We don't want to wash our hands in oil, right? I mean, that would just kind of make a bigger mess. But what we can do is take our hand that's still dirty and we can mix it with soap. So what we're doing is, when I say soap is being mixed with our hand, we're going to take our micelle, which is getting a little sloppier. So this is our micelle. We're going to let the soap that is mixing with water to form a micelle. Okay, you squirt some soap into the water, a bunch of micelles form. Now the micelles are going to interact with our hands, and our hands are going to be clean. Now, why is that? Well, the water couldn't productively dissolve or interact with the grease, but the micelle could. The micelle has these hydrophobic tails buried on the inside of the sphere, and those hydrophobic tails will dissolve the grease. So the grease is tucked inside of our micelle sphere, but the micelle is still overall soluble in water, and it washes away in water. And we have soap. Pretty cool. And it's actually a pretty simple source. We take fatty acids, and fatty acids are pretty easy to obtain from fats. So if you take fats and you kind of break them down through a process called saponification, soap making, if you will, you can give rise to these fatty acid detergents. Now, soap chemistry can be a lot more complicated. There are some pretty sophisticated soaps out there, but by and large, this was the most basic and kind of earliest soap. In fact, if you ever handle a really strong base like just neat sodium hydroxide, if you get some on your skin or a concentrated solution, just a little bit. If you put too much, you'll burn and bad stuff will happen. But if you get a little bit on your hands, you kind of rub them together and you're like, ooh, there's kind of a strange lubricating feeling. Well, what's happening is there's a subtle saponification reaction where the oils and the lipids and the triglycerides on the surface of your skin are being converted into little fatty acid detergents. You're kind of converting yourself into a little bar of soap. So you could just take yourself over to the sink, wash your hands, wash away the dirt and the grime and the oils, using your own body as a soap. I know, super gross, right? But it's kind of interesting. In fact, this was how soap was discovered. It was very well summarized in the movie Fight Club, where they talked about it's kind of, I mean, they robbed like some fatty tissue and actually converted it into really nice bars of soap. It's not like I'm not giving away a whole punchline of the movie, but it's kind of interesting. And they talk about how the way this was discovered was in kind of some tribal parts of the world where human sacrifices were done. They would kind of decompose the bodies using a reagent called lye. And lye is just a combination of really strong bases that can induce saponification reactions, amongst other things, to decompose bodies. Well, what happened was they would decompose the bodies using lye and kind of dump them in the river. And what happened was people noticed that, hey, if I wash my clothes in the river downstream of a human sacrifice, my clothes come out really clean, which is counterintuitive. Now, what's happening is they're using the soap molecules from the sacrificed person's fatty acids to make a bunch of micelles, and those micelles clear away a bunch of the dirt and the grime. So I guess a sad history, but super useful chemistry, and fatty acids are readily abundant from numerous sources, not human sacrifices anymore, thankfully. But anyway, that'll wrap up Module 4 material, and we'll start talking about chemical reactions in Module 5. But anyway, hopefully you enjoyed this wrap-up lecture on